In this video, we will talk about mass moment of inertia, topic 10.8. Mass moment of inertia. Explain the concept of mass moment of inertia, MMI, and determine the mass moment of inertia of a composite body. Now, this concept is actually more applicable to dynamics than statics. So we will just stick to the definition, simple definition of what is mass moment of inertia. So the formula to calculate the mass moment of inertia about an axis is r squared dm. Now, where r, so what? So if we have this small area, if we have small mass dm, which is located at distance r from the axis, and we would like to calculate the mass moment of inertia of this shape about this axis, then it's r squared dm, where distance r is measured in meters and mass in kilograms, so its unit is kilogram meter square or slug per slug foot square. The parallel axis theorem can be applied to both mass moment of inertia and area moment of inertia. Now, this moment of inertia is different from area moment of inertia in the sense that for area moment of inertia, it is resistance to bending, and mass moment of inertia is resistance to angular acceleration. So if you look at this flywheel, then majority of the material of the flywheel is actually hollow here, and the heavy metal is being located away from the center line. So more material is concentrated away from the center point. And when it's done in that way, the mass moment of inertia of flywheel increases. And as a result, it offers more resistance to angular acceleration. So when look at this fan, so when torque M is applied to a fan blade initially at rest, its angular speed begins to increase. So when the torque M is applied by the motor, the speed of the fan blade increases. Now, for the given moment or torque, what will be the speed of this wheel at certain time depends on the angular acceleration alpha, which in turn depends on the mass moment of inertia. And the formula for that is T is equal to I alpha, where T is either torque or moment, I is the mass moment of inertia, and alpha is called the angular acceleration. And in order to design the components, or in order to select the motor or required torque, we can if we have some idea about the angular acceleration, then we multiply that with MMI, we get the required torque value. So the MMI is often used when analyzing rotational motion. This is mostly in dynamics, not for statics. Okay, and the formula to calculate mass moment of inertia of this small mass dm at distance r from the axis is r square dm. So the overall moment of inertia of this entire blue shape is integral of over mass. So it's I is equal to integral r square dm, and the unit is kilogram meter square or slug feet square. Same parallel axis theorem and radius of gyration concepts are applied to MMI as well. So we have studied about them with area moment of inertia, but these are the same concepts. Parallel axis theorem and radius of gyration, as well as the composite bodies concepts are applied here. Now let's quickly scan through one example, and then so for example, in this pendulum, we are being given the dimensions and the mass of this rod as well as the plate of the pendulum, and we would like to calculate the radius of gyration about axis O. So imagine that this axis, and relative to that, this pendulum is being rotated. So we would like to know what is the radius of gyration relative to this point. So for that, first we need to calculate the mass moment of inertia of the plate about O. We need to calculate radius of gyration, mass moment of inertia of the rod about O, and then we can apply radius of gyration equation, and that's being done here. So step number one is the overall centroid y-axis of the shape is determined using composite theory. So this is the overall centroid of the shape. We have studied this in chapter 9, how to apply this equation, and that's 1.178 meters. And then the formulas are applied for like the plate as well as the rod. R for rod, P is for plate. So moment of inertia of the plate is 1 by 12 times this dimension square plus the other dimension square multiplied by mass of the plate. So that's this formula. And then this is parallel axis theorem being applied. So this is the overall moment of inertia of the plate about O. Same goes for the rod. It's 1 by 12 m L square. That's the formula. So this formula for the plate is 1 by 12 times mass times width times width square plus h square. That's the formula that's being applied for the plate. And for the rod, it's 1 by 12 ml square. That's the moment of inertia of the rod about its own centroid. And then this is the parallel axis theorem part. Okay, so for parallel axis theorem, it's I is equal to IO is equal to IX plus A. Instead of A, now it's MD square. Remember in area moment of inertia, we had AD square, now we have MD square. So that formula is this formula here. And then the radius of gyration is calculated using this equation. That first we calculate the overall moment of inertia of the shape about O, which is IP plus I rod. And then calculate the radius of gyration as square root of this IO divided by total mass, which is plate plus rod. And that's 0.746 meters. So what it means practically that if you replace this total pendulum by a point mass of 8 kilogram, then the mass can be rotated at distance k, and that will have the same moment of inertia as that of the pendulum. And this will help us to simplify the pendulum as a point mass, which actually plays very important role when we solve dynamics problem. Okay, thank you.